Okay, students, today what we have to do, I will be covering with you the how the Fermi energy level varies for intrinsic semiconductor. Okay, as you can see this particular band diagram, in this you have two bands which is shown by blue color, that is valence band in case of pure semiconductor material, and other is the conduction band shown by the red color for the intrinsic semiconductors. And hence you can see there is a forbidden energy band gap represented by Eg symbol, but we can see here Fermi level is lying in the middle of both Ec, that is the bottom edge of conduction band, and Ev, which is the top edge of valence band. So the Fermi level in case of intrinsic semiconductor, it lies in the middle of the forbidden energy gap, because this is the half of forbidden energy gap. So we can say EF is equal to Eg by 2 for the intrinsic or pure semiconductor material. Then comes a very important law, that is a mass action law, which states that like addition of n-type impurities decreases the number of holes, because we are adding group 5, or you can say pentavalent impurities, and due to which electron concentration increases, and hence number of holes decreases below a level. Similarly, addition of p-type impurities decreases number of electrons below a level but increases the hole concentration, because we are doping group 3 elements, and every time we are doping it, what happens? One electron remains unbonded. It does not share a covalent bond. Because of that, a hole is created extra. And as it has been experimentally found that under thermal equilibrium, this is a statement of mass action law. It states that under thermal equilibrium, that is T equal to 0 Kelvin, you can say, for any semiconductor, the product of number of holes and the number of electrons is a constant, and it's also independent of amount of doping. So this is a statement for mass action law. That's it why this relation is known as mass action law, given by this particular equation, where you can see n dot p is equal to ni square, where n represents the concentration of electrons in semiconductor, and p represents the concentration of holes in the semiconducting material, and Ni is your intrinsic charge carrier concentration. So, as stated by this particular law, under thermal equilibrium, for any semiconductor, product of number of holes by P, number of electrons by N is equal to a constant, and it is also independent of amount of doping. So this mass action law will be used in every derivation while finding out the concentration of electrons and concentration of holes for intrinsic and extrinsic semiconductors. Then comes the concept of energy band gap, Eg. So what exactly is band gap? It's a minimum amount of energy required to excite an electron from valence band to conduction band. Whenever we are applying energy, see, we have energy band diagram like this. We have conduction band here, and then comes the valence band, and then there is a Eg band gap. So minimum amount of energy, if electrons are present in valence band which is fully filled, we need to apply some energy to electrons in valence band such that they can jump to the conduction band, and that minimum amount of energy which can allow the electron to leave valence band and go to conduction band is actually called the Eg, or you can say energy band gap for a semiconductor material. And Eg is a characteristic of the material. If you know the Eg value, if Eg value is known, then easily you can know which kind of optically active material it is. So it is a characteristic of the material. It's unique for every material. And motion of valence electrons, free electrons in the valence band, is described in terms of a fictitious particle hole. Now comes the concept of another charge carrier, which is a hole. It's actually an imaginary particle. It does not exist actually, but yes, whenever electron is leaving its position and moving on to the conduction band, it leaves a vacancy. A vacancy is being created. That vacancy is termed as a hole. That vacancy is called as a hole, which is a fictitious particle. It has charge, it has mass, but the mass is equal to the mass of electron, which is equal to 9.1 into 10 to the power minus 31 kg. The mass is equal, but the charge on hole is positive, and electron charge is negative, hole charge is positive. But yes, they bear a equal value, that is 1.6 into 10 to the power minus 19 coulomb. So value is same, but the nature of charge is different or opposite in case of holes and electrons. Energy required to break a covalent bond at 300 Kelvin in germanium crystal is 0.72 electron volt, and for silicon is 1.12 electron volt. These are actually the values of energy band gap for these crystals, silicon crystal and germanium crystal. So same, whatever energy is required to break the covalent bond, this is also given by the value of Eg. Okay. Now we will be discussing how the electrons, how the holes are playing role in the electrical conduction process and how it is going to work. So let's start with that. Holes in electrical conduction. Electron at a lower energy level makes upward transition to a vacant level, because like we have again I'm drawing the diagram for you people. It's valence band and conduction band. Valence band is fully filled with electrons. Electrons are present here, right? So electron, what is happening? Electron at a lower energy level makes upward transition to a vacant level. As electron moves up, vacancy moves down. So what is happening actually? There are electrons here, 2 million electrons. Whenever a position is being emptied by electron while moving to the conduction band, they are moved to the conduction band. That particular vacancy is called hole. Again, the electron which are present just adjacent, or you can see say at the lower level, with respect to this vacant position, they try to occupy that position. They jump to a higher level. Because of that, electron is occupied at this particular position, but the lower down position is being occupied by the hole. So hole is created, hole is going downwards, but the electrons are moving upwards. And you can see from here that electrons and holes are moving in an opposite direction, because as electrons are moving upwards, the holes are created downwards, because every hole position is being occupied by the lower occupied electron. So lower electron tries to occupy the upper hole position, and that particular hole is replaced by electron, and then hole is created in the lower level as that position is being left by some other electron. So this is the way it is being explained here. As electron moves up, vacancy moves down. Electron moving up, but vacancy moving down. Hence both moves in an opposite direction in valence band. So both have an opposite direction also. Instantaneous current produced by one electron moving at a speed v subscript में k, and that particular current was given by I is equal to minus e vk, where vk is the velocity of the electron, speed of the electron, and e is the charge on electron, which was equal to 1.6 into 10 to the power minus 19 coulomb. Then comes the current set up by motion of many electrons in valence band. If many electrons are moving in valence band, what will be the current due to that? Obviously the summation of all velocities, and charge will remain same. So I is equal to minus e summation vi. Then for a completely filled band, resultant current is 0. If valence band is fully filled, if this band is fully filled, obviously no electron will be going towards the, there is no transition towards the conduction band. If there is no electron in conduction band, there will be no net current, no current, and because of that we have written total I is equal to 0, which is equal to minus e summation vi equal to 0. If we talk about, we have taken a case for a completely filled band, completely filled valence band actually. Okay, so I is equal to 0, or I is equal to 0 is equated by adding the velocity of a single electron also. Then it comes out to be that summation vi is equal to minus of vk, and this is for I not equal to k. If we are talking, if we have left one electron in the we are considering the one electron is moving at speed vk, but others are at rest because it is fully filled band. So at that particular point, the velocity of one electron will be equal to summation of velocities of all electrons, but with a negative sign because they are moving in the opposite manner. So this states that significance of this particular equation. Let's talk about significance. if kth electron is absent in the valence band, see, this is not present in valence band, that is why it is playing a role in the conduction process, or it is relating to generation of current. Then sum of velocities of remaining electrons is minus Vk. So summation of remaining electron velocity is equal to minus Vk. If vacancy is to be given the status of a particle, that is we are talking about a hole, a mass is also ascribed to it, and in solids, electrons experiences forces due to atoms and other electrons. Whatever is present in the lattice, crystal lattice, they all are exerting force onto the charge carriers. Hence, F is equal to, by Newton's law, F is equal to me star A, where me star is the effective mass of electron. So this is the equation which is stating that if any one electron is free to move, then its velocity is equal to summation of velocity of all the electrons which are completely occupying the valence band, and obviously the negative sign due to the opposite motion of the electrons or charge carriers. So this is all about the holes in electrical conduction. Now let's come on to our next topic, which is a generation and recombination. So this is a very important process, because based on these two processes, our many devices in semiconductors are based. Like if we talk about solar cells, they are highly dependent on the principle of generation of charge carriers. But if we talk about light emitting diode, that is LED, they are actually based on the recombination principle. Okay, so I will be talking about these things in the future slides. So let's start and understand these processes, what happens actually. Okay, as you can see this picture here, it is mentioned valence band, and this is the conduction band, and then comes the energy band gap, which is mentioned by Eg symbol. This is Eg, and then you can see whenever electron hole pair gets break up, whenever there is a breaking of electron hole pair, electron jumps to the conduction band, and holes remain there, and this process is called generation. And you can see how it will happen. See, covalent bond of electron hole is getting apart, or they are breaking. So when does it happen? On the application of some thermal energy or electrical energy. So covalent bond plus thermal energy is producing actually electron hole pair. This process is called generation, and this is a equation of generation. And at any temperature T, N is equal to P, because if we are talking about an intrinsic semiconductor, obviously at every point in intrinsic pure semiconductor, electron concentration is always equal to the hole concentration. That is the equation for that. Electrons move in the conduction band while holes move in the valence band, and their motion is random unless and until an external electric field is not applied. External electric field is just for making the motion directional in nature. Else, there will be a motion because of free electrons, the free holes, but that will be highly random. So we are talking that if external thermal energy is being applied, electron hole pair gets broken up, and due to that, electron jump to conduction band, and this process is called a generation process. Okay, but what happens in the case of recombination? Recombination is just the opposite process of generation. So electron in conduction band may lose its energy due to collision with other particles in lattice and fall back into the valence band. So they are losing energy due to collision with other particles and electrons, and they are falling back into the valence band. This is, like, you can see this arrow coming back to valence band. And whenever a free electron falls back into valence band, it merges with the hole. They are occupying again the same vacant position, and this particular process is called recombination, coming back to the valence band. So obviously whatever energy was being absorbed for going to the conduction band, that is being released when they come back to the valence band. So electron plus hole, when recombines, they form a covalent bond and also generate some amount of energy is being released here. Also, the light radiation can produce electron hole pairs in semiconductor. Like we talked about thermal energy above for generation process, so light can be also another source. Like we talk about the photoelectric effect. There the condition is H nu must be greater than or equal to Eg. That the incident energy must be greater than or equal to the energy band gap of the target material. So optically generated electron hole pairs are responsible for working of LDRs, light detectors, photodiodes, optical detectors. Okay, so this generation or recombination process is actually playing a lot of role in the application devices of semiconductor material. Now let's discuss about the intrinsic conductivity in the pure semiconductor material. So what happens? Intrinsic density, intrinsic concentration. This means pure concentration in case of pure semiconductor material. It's given by N equal to P, because electron concentration is equal to, electron concentration represented by N symbol is actually equal to hole concentration, which is represented by P symbol, and it's further equal to a new constant which can be equated to a Ni, which is intrinsic charge carrier concentration. Under thermal equilibrium condition, charge carriers move randomly in valence band and conduction band because no external energy, no external field, no external thermal or optical energy is being applied onto the material. At temperature T, they possess average kinetic energy, which is given by half mv square kinetic energy, but due to the thermal, we can say the application thermal energy. So half mv th square is equal to 3 by 2 kt, which is a thermal kinetic energy, and Vth represents the mean thermal velocity of the electrons or charge carriers. Okay, so whenever a potential difference is applied, you can say whenever you apply some electric field, equilibrium gets disturbed, and we say that electric field accelerates electron and hole, but their motion is hindered due to the lattice interactions with the lattice vibration. So this is the process, like electric field is trying to accelerate electron and hole with charge carriers, but still there are some collisions and interactions with the other lattice sides. So due to that, their motion gets hindered, it is getting obstructed. In steady state condition, there is a net movement of electrons in a direction opposite to that of the electric field, and movement of holes in the direction of the electric field. So in the steady state condition, net move this is like it must be electrons, yeah, in a direction opposite to that of electric field, where holes, I told you previously, electrons were moving upward but holes were moving downward. So actually the current conduction direction is governed by the holes direction, so current direction will also go in the downward side. So there is a net movement of electrons in a direction opposite to that of electric field, and electron holes move in the direction of electric field. Okay, this net movement of electrons and holes is called drift, and corresponding velocity is the drift velocity represented by Vd. Okay, so whatever, if we apply external electric field, electrons gain some kind of velocity which is given as drift velocity, and due to that this particular velocity is called drift velocity, and the current flowing due to the movement of these electrons is called as drift current, id. You can say drift current, which is generated due to the application of external electric field. Drift motion is directional and causes drift current or conduction current to flow. So it is highly directional because we are applying some external electric field. So let's deduce the equation for the drift current and drift velocity, and what is the value of conductivity for pure semiconductor material. Drift velocity, see, Vd is given by mu times capital E, where mu is the mobility of the material, of electron or hole, whatever we are talking about, and E is the, capital E is the applied electric field. Okay, so current density due to electrons is given by Je equal to NeVd. Again Vd, let's put the value of Vd from equation number 3. Vd is equal to mu times capital E, hence Je is equal to Ne mu times capital E. Then current density due to holes, Jh, is given by Pe Vdh, because we are talking about the holes, so I have put a subscript, that is Dh, and then on putting the value of Vdh, Pe mu h times of capital E. By using the Ohm's law, we know that current density is given by J is equal to sigma times of capital E, where sigma represents the conductivity of the material. Okay, now on comparing these three equations, 4th, 5th and 6th equation, we can see that sigma is coming out, sigma is coming out to be equal to, see, if I see Jh is equal to Pe mu E, J is equal to sigma times E, then obviously sigma conductivity for the electron is given by Ne mu E, because E is common both here and there. So these terms gets equated. So sigma is equal to any mu E, and similarly conductivity for holes come out to be equal to PE mu H. And total current is given by the summation of current due to electrons and current due to holes. So I is equal to IE plus IH. And similarly current density, total current density is equal to JE plus JH. So it will be equal to IE. We know that current density is equal to current per unit area. Okay. So IE plus IH upon A, which is cross-sectional area of semiconductor crystal. But we know the value of JE and JH from equation number 4 and 5. So equation 4 and 5, adding these two equations, we get the value equal to this thing. And intrinsic conductivity, total intrinsics, we are talking about all the total things. Okay. Total intrinsic conductivity is given by sigma is equal to sigma E plus sigma H. Sigma E is given by any mu E, and sigma H is given by PE mu H, where N and P are the concentration of electrons and holes respectively. But we know that N is equal to P, which is further equal to Ni. As I showed you in the previous slide also, we are talking about this particular intrinsic semiconductor, equation 1. Using that, so we can easily say that for intrinsic semiconductor, we can say N is equal to P. So N can be taken out common. Either put P, either put N. I have put P equal to N here in this particular equation, and I have taken up N as actually equal to Ni. Ni is taken outside as a common, and then E, charge on both the electron and hole is same but with the opposite sign, but still we have taken E here as a common. Then comes in the bracket mu E plus mu H. So sigma is equal to Ni mu E plus mu H for the intrinsic semiconductor material. Now further I would like to mention that sigma is a function of temperature T. Why so? Because sigma is depending on Ni, and we know that intrinsic carrier concentration does vary, and whenever we increase temperature, the charge carriers get excited to the conduction band, and which in further, whenever the charge carrier is moving to conduction, electrons are moving to conduction band, it results into the conductivity. It results into conduction process. So that is why I have written sigma as a function of T is dependent on the Ni as a function of T. So it is directly depending on the temperature T. Okay class, thank you so much. Further we will continue in the next lecture. If you have any doubts, you can post in the comment section, and please do like, share and subscribe my videos.